Swayam Prabha. Digital India. Educated India.
So, some of you have been listening to me talk about this stuff for the last few years. And every time I think when I put the slide up, I end up talking about classical mechanics and then essentially saying, okay, I didn't have time, so I cannot do the quantum mechanics. Well, this time it's going to be different. It's going to be pretty much all in the quantum mechanics. Okay. And as you can see, that actually has to do with this reason of saying that we're going to be talking about some interesting dynamical properties here. This work actually got started a few years ago, I mean, pretty much during the COVID time with Priyanka and Shivabrat, but then Aanchol, who's done most of this work, I'm going to be reporting about now. So let me start with a very basic question. So in usual ways in chemistry, when we think about transition states, we think about index 1 saddles, and that's pretty much the gold standard, right? This is how we think. But then it's kind of hard to believe that on incredibly multidimensional potential energy surfaces, there would be only index 1 saddles. I mean, there's got to be higher index saddles, and there's going to be much more complicated topology of the potential energy surface. And the question is, do they play any role at all or not? So the key point here is that if you go beyond this, I mean, if you have index 2 saddle or index 3 saddle, then how do you even think about transition state theory, first of all? I mean, you can't even write down an expression for transition state theory. Because the way we write the expression for transition state theory, either way you derive it, has something to do with it being an index 1 saddle, not higher index saddles. Now, of course, all of you might immediately raise your hand and object and say, oh, there's this great theorem called the Murrow-Leitler theorem, which ensures you that, you know, if there is a higher index saddle, there are always lower index saddles which are going to connect. Well, true, as long as if you are not a believer in dynamics, then that's perfectly fine. Once it's allowed for dynamics to do its magic, Murrow-Leitler theorem really is of not much of help, actually. And it turns out there are enough violations of Murrow-Leitler theorem anyways. So I hope to be able to show you the complexity of the dynamics in this particularly simple model. Oops, okay, that's going in the wrong direction. So are there actually, I mean, these systems have been looked at, and people have looked at in various sort of contexts. This is a pretty old paper actually by Hauck, you know, I mean, it's 30 years back when they were looking at this very interesting reaction. And they basically said that we find this higher index saddles in this system. And they basically ended by saying, we have to study the dynamics of motion about this surface in order to understand this reaction. And this was 30 years back, essentially. Even before that, Broilet and Schaefer, looking at Woodward-Hoffman, they said that, you know, if you think about the conrotatory, which is thermally allowed, you know, this is a index 1 saddle transition state, but the disrotatory, which is not allowed, actually there is an index 2 saddle that can do the job, but, you know, that's not a transition state. So let's forget that. More recently, Todd Martinez and his group, they have looked very closely at the conditions when Woodward-Hoffman is violated, for example. And it actually happens in a mechanochemical setting. And it turns out that there is interesting situations where the index 2 saddle comes into play. So, in fact, there's a very wonderful perspective or insight by Suits and Parker a few years ago, where they were commenting about a reaction where when these people excited the carbon dioxide, they basically ended up getting carbon and oxygen. Okay, and Suits and Parker actually argue that this can only happen if you have higher rank saddles in the system. And as they point out, in the roaming mechanism, which is sort of now, you know, so everybody's familiar with it, they basically say that the conditions for many of these non-minimum energy path processes is a second order saddle point, and there's a connection between this and the existence of roaming mechanisms. Okay. So as you can see, they illustrate that with this sort of these hills, if you want, and including, you know, index 1 saddle, but also index 2. So the process dynamically looks like, we look at hot systems, enough energy, they're actually above the hill. They are kind of like this wingsuit diver, right? I mean, they're going over this and they're trying to explore this incredibly complicated potential energy landscape. And the question is that if you do the dynamics, and actually what are you going to see in these systems? In fact, the narrative sort of has been flipped, if you want. There are a couple of recent papers where they actually are thinking about taking advantage of these second order saddle points. In fact, one of them argues that if you have a second order saddle point, there's an interesting way to actually convert them to an ordinary transition point and use it as a design principle for photo switches, which are much more stable. There is another one which is also pretty interesting, since this actually has to do with rotaxanes, where you have this process where you have an axle, for these molecular systems, you have a bond about which you can have a rotation, and this particular thing, this ring can flip across. It's basically a macrocycle. And it turns out that there are two ways sort of thinking about it, and this sort of refers back to the sequential and concerted thing, which is heard, early on, that you could actually have the bond rotation and the sliding along this axis in a concerted fashion, or it could happen in a sequential fashion. And it turns out that there are some very interesting design principles that come from it. And as these people say, besides this fundamental interest, these movements, if they can take place asynchronously or synchronously, are important to take synthetic molecular machines to a higher level of sophistication where you can actually control the motor unit. So there's seemingly a lot of interest here. So let me sort of summarize a couple of questions that we're interested in. So one is, of course, is concerted versus sequential. It turns out, of course, it's inherently a dynamical distinction, and we cannot sort of just look at the potential and decide on that. They are breeding grounds for non-statistical dynamics, actually, these second long saddles, if they occur. So there's this open question that if you have higher index saddles, and let's assume that they are going to contribute non-trivially to the rate processes, then how do you actually write a transition state theory-like expression which includes contribution from these higher rank saddles? And that's a particularly challenging problem. And of course, these folks here from George Haller and George Jaffe and Tamiki, the Japanese group, Tamiki and Nagata, and then Ezra and Steve Wiggins over in Bristol have devoted considerable amount of efforts to try to get this in place. There's also our own organizer, Raj, and my ex-student Manikandan have collaborated on some of these important things that happen in second order saddle points and why they are dynamically important. There is, so I'm going to talk about dynamics, but I couldn't resist from making this say. There's a recent article by Howe, Hoffman, Stephen, and these folks, and they talk about whether the time has come for organic chemists to start pay attention to dynamics, okay? And what they say is very interesting. They say 50 years later, we may be close to having the language in physics and chemistry and computing power to understand dynamic effects, and not quite yet. I mean, this is from just last year. Right? But the interesting part to us theoreticians who do dynamics is that organic chemists are beginning to notice this. They're beginning to notice that they cannot make these, sort of blanket assumptions that they've been doing for decades now. And, they have to look at things carefully. Right. So the question, of course, is sequential or concerted. So if you think about this sort of a simple potential energy surface, if you think about a reactant and a product, you've got some intermediates over here. Usually when you think concerted, you're thinking the process just going straight from the reactants to products without visiting these intermediates. The other, of course, is sequential, where it does get into the intermediates and then finally ends up with the products. It turns out that this concept, this idea, in fact, even way back in 1999, Zubail wrote that acceptance of one mechanism over the other has to be handled with extreme care. And it turns out there is lots of examples where people actually have worried very carefully, including some very beautiful work by von Doering and Berson, where they think about what exactly is this mechanism, how do they nail one way or the other. Okay. So in since this is sort of, I think there was a hint by Andrew in answering my question towards the end. Ken Houck actually a few years ago realized that they were looking at a whole class of Diels-Alder reactions. And they realized that if they made a hypothesis, if you will, that if they think about the bonds being formed, if these are multiple bonds being broken and formed, if they look at the delay time between the formation of the bonds, and they sort of, compute these delay time distributions, which is shown here, that if they think about this delay time, they put a threshold, which is nothing but the time threshold that comes from Eyring's theory, which is by the way, this is a typo, it should be inverse of this. It's about 60 femtoseconds at room temperature. And they said that if the delay time is less than that, then, for all practical purposes, we should think of this as concerted, but he said, qualified it by saying it's dynamically concerted. Okay. And of course, the rest is going to be stepwise or dynamically stepwise. So this notion was put forward by Hauck and his group. They've utilized it, and they have understood a whole class of reactions by using this particular idea. But all that work, of course, has been using classical dynamics. And therefore, there is this fundamental question that arises. Do you have even a notion of quantum dynamical concertedness? I mean, what does it mean to say even quantum? So will this dynamically concerted notion actually survive quantization in some sense? And it turns out, in fact, they in their one of the reviews that they wrote fairly recently, they said, we note, however, that this timing borderline is an arbitrary but a reasonable boundary. Okay, in other words, this kBt by h or inverse of that is a reasonable thing, because that actually has to do with the time scale it takes to cross the transition state in some sense, which an important transition state. And so it's a reasonable time scale, but is there a dynamical basis for that time, that time's threshold? This is not clear. Okay, but this, but that's what they use. So there is actually three clear questions one can ask. One is there a dynamical foundation for this delay time distribution? The second is, can you generalize this to index 2 saddles or higher index saddles? And third, is there even a notion of a quantum delay time distribution? Okay. Ultimately, we may run classical trajectories, but ultimately we have to ask, if you do quantum mechanics, is classical mechanics going to hold up or not? And this is extremely important, because there are more than one way in which quantum mechanics has surprised people. Okay. So we wanted to look at this a little bit more carefully. All right. So I'm going to talk about a fairly simple model. It's a double proton transfer model. It's a model Hamiltonian. It's just 2 degrees of freedom, but it has essentially the essence of this problem, in the sense that it has basically 2 hydrogens that can move. And if you want to visualize it in this porphyrine molecule, they're sitting like this, and a concerted motion would be when they go across like this. And a stepwise motion would be when one of them goes and the other one goes. Okay, this is the idea. And the rank 2 saddle is when both of these hydrogens are sort of at the center of this ring. Okay. And it turns out that Smedacina and Fernandez-Ramos actually did a lot of work, and they really parameterized this Hamiltonian, this form, and they provided, and they said essentially there are a couple of parameters that will capture the essence of this, and you could tailor these parameters to a large class of these molecules. And so here's the potential. Basically, it is 2 double wells, which is representing the 2 protons, and they are coupled by this sort of symmetric, this x squared, x. What x, s, and a are the symmetric and antisymmetric combination of these 2 proton motions, essentially. Okay. Now, first question is how. So, in the case of Hauck, they are basically looking at temperature dependent canonical stuff. So it was natural for them to use the h by kBt sort of as the threshold thing. Here we are going to do microcanonical. So, there is no t here in some sense. So how do you actually define? Well, the way we take this clue is we say, well, okay, let's look at this Hamiltonian that we have. We were going to linearize it about the rank 2 saddle that is there. And essentially, it turns out that there is a very nice theory by Haller, who were doing this work about rank 2 saddles and escape rates. They say that essentially there's a time scale that you can associate with escape across from this rank 2 saddle if you want. And it's sort of the mean of the curvature of the 2 directions if you want. And we therefore we said, okay, this is reasonable first guess at what this threshold time should be. Basically, this is a time, sort of the fastest time scale you have for the system to leave this rank 2 saddle area. Okay? And so this is how we compute this distribution. So what we do is we start off, for example, we could start at the rank 2 saddle, or we could start at the reactant. We basically take an ensemble of trajectories, we propagate them both forward and back in time, and when look at, suppose it actually goes and it, let's say, enters the intermediate region first. So we start a clock, and then when it leaves the intermediate and enters the product region, we stop the clock, and this difference is essentially the delay time. Okay. So here's an example of a classical delay time distribution. So this is basically trajectories being started actually on the rank 2 saddle. It's a Gaussian distribution, basically a coherent state if you want. And they are at an energy which is actually above the rank 2 saddle, right? So the rank 2 saddle is at an energy 1. That's a good number to remember. And this distribution is being shown at about a quarter, 0.25 above the rank 2 saddle. And these are reduced units, so this can be a pretty large energy actually. And what you see here is, in fact, the kind of the distribution that Hauck would see, for instance. And you see there's a threshold time. So I forgot to tell you, this threshold time for the parameters we are using, this is around 4, somewhere between 4 and 5. So we use that as the cutoff time. And if you look at this, it basically tells you that this is the fraction which is dynamically concerted, and the rest is essentially sequential. Okay, so far so good. And we say, all right, now that we have this, let's ask this question. That was at a particular energy. If I look at the fraction of dynamically concerted trajectories as a function of energy, as I go up and up and up and up above the rank 2 saddle, what does this fraction look like? Well, if you look at, for a particular parameter value, this D, which is there in the coupling, by the way, which also changes the shape of the potential. So it's an important parameter. If you can look at this, this is all above the rank 2 saddle. This is going up and up and up, and you can see that there are these oscillations. And these huge oscillations that are happening. This is the blue is the curve you want to look at, dynamically concerted. And you can see it's somewhere below 50% and actually crosses over. If you just flip the sign on D, it changes the shape of the potential, but keeps everything the same. What you end up seeing is that there's a completely different behavior. Just to give you a hint, essentially, for example, if you look at a particular energy and you ask, what is the phase space, since this is classical dynamics, what does the phase space look like? They're actually quite different. And so we know, thanks to the work by Steve Wiggins and Greg Ezra and Gog Haller and Jaffe, that there are certain stable and unstable manifolds which are actually responsible for the behavior. But I will not get into that right now. Let me actually basically make the statement that the shape of the potential energy surface actually has an extremely strong effect on the extent of dynamical conservativeness. Okay. So the $1,000,000 question, quantum dynamical conservativeness. Well, how are we going to do this? So first of all, there is a fundamental problem. Because in quantum mechanics, the usual way, you would of course you would compute, you would solve the Schrodinger equation, you have a wave function and it's delocalized. And there's no meaning. What do you mean by saying that one bond was formed and the other was bound? I mean, that's a very trajectory notion. And so you cannot use wave functions to really do that so straightforward. But it turns out that Craig Martins, some years ago, actually gave a method which is perfectly suited for what we want to do. This is actually called as entangled trajectory molecular dynamics. Basically, what you do is you do classical mechanics, but then you lift it into the phase space by actually propagating the von Neumann equation in the Wigner representation. And therefore, you are following the Wigner function. And it turns out that this is actually something that can give you a lot of things like the N-phase dynamics, the tunneling, entanglement, decoherence, all of those things to leading order in Planck constant. So it's actually a very good, perfect method for us because it actually gives us quantum trajectories. And now what we can do is we can actually start with a classical distribution, the results that I showed you. We can take the corresponding Wigner distribution, propagate classically and quantum mechanically using the Wigner by solving the quantum Liouville equation, and then see what differences are there. The picture that I want to sort of convey here, or rather here, is that in classical mechanics, when you look at the evolution of phase space density, each initial condition gives you a trajectory, and these trajectories are statistically independent. Okay, they are independent of each other. The difference here, when you do a Wigner function, of course, is that these trajectories, quantum mechanically now, talk to each other, they're entangled. So in other words, you don't have independent trajectories, but what you have is, you have trajectories, you have a classical part, but then you have a part that actually depends on the Wigner function, entire Wigner function itself, so it's highly non-local. So this, you get entanglement, it's there, it's for the ride, okay? So these are not independent. So these trajectories are no longer independent, they're talking to each other. Okay. So that's good, that's wonderful. Now let's see what happens with this. So here's the same part of this dynamical concerted behavior I showed, but now I'm actually comparing the classical and the quantum. So here's the classical bit which I showed, which is in black. And here's the quantum, the ETM, the entangled trajectory molecular dynamics part. Okay, so the same energy. This is how the distributions change. And you can see that there are regions where you actually see nominal differences, 10 to 15% difference. These differences can sometimes be crucial. For example, this is, you would say, is majorly stepwise, whereas the ETMD or the entangled trajectory would actually say that this is probably more leaning towards dynamically concerted. There are, of course, regions where the agreement is excellent. For example, if I didn't tell you that this is a quantum or a classical, you would think that these oscillations in this peak is something, as we also anticipated, going to be a big quantum effect. But as you can see, the classical and quantum are on top of each other on that peak. So, this is actually a lesson. So if you see oscillations in your calculations, and if you see some interesting peak structures, just don't jump and say that this is quantum interference, because it's not. Classical will reproduce it to the T. Okay, that's the important lesson here. So, but there are differences over here. Now, the question, of course, is what is the origin of these differences? Where are these differences coming from? Well, it turns out actually what I showed you was the more conservative difference. It turns out if you vary the D, remember this parameter that changes the shape of the potential, you can actually make these differences pretty large. So, for example, here is this dynamically concerted fraction. As you vary this D from being negative to positive, okay, and for example, right here, you can see that the difference is almost 50%. So that is a pretty large difference. So basically, quantum mechanics is now saying that this is essentially dynamically concerted, okay, whereas the classical will predict something different. So all of these trajectories were actually launched from the reactant part of the potential here. Now, if you take a look at this, this particular energy, this particular D at some particular energy, you actually see that the phase space actually is far from being chaotic. It's actually mixed regular chaotic. It has structures there. And we said, okay, why is there this particular difference? Remember, there are also certain Ds where this difference is almost non-existent, actually. So it's not a monotonic difference between classical and quantum. So it's highly non-trivial. So what we did was we went back and looked at some of these trajectories which, like Houdini, changed their character from sequential classically to concerted quantum mechanically. Right? And what is interesting is that here are some examples. Here's a classical trajectory which clearly starts from the reactant, actually spends a lot of time in the intermediate, but eventually gets over to the product. It's clearly a sequential process. But for the same trajectory, same starting condition, the entangled trajectory, the Wigner representation actually shows that this is basically a dynamically concerted process. Here's another example which is even more extreme. The classical is clearly sequential, but the quantum part, it's just a straight line screaming across from the reactant to the product. And Barry Carpenter would be extremely happy to see this, because this is what he would call as directed motion across this rank to saddle, or what he called dynamic matching. Okay. So it turns out, so we said, why do we see these kinds of trajectories? What is happening? So the threshold time for classical is much larger than the threshold time that we have taken. But the quantum is almost close to the threshold time, or much smaller. Well, it turns out these regular islands that I showed you, if you go and look at this, if you look at this, if your initial condition happens to be here, this is the reactant part of the phase space. If your initial condition happens to be here, you would be trapped. You would be forever trapped. You would never get out of there. But what happens is the quantum actually gets out of there. Remember, this energy is actually far above the rank 2 saddle. There are no barriers there. What you're seeing here are perfect examples of what are called dynamical barriers. The dynamics generates these barriers. So you are energetically above the rank 2 saddle, far above, but classically you would be trapped forever if you start there. But the quantum, of course, will always find a way. And this, in fact, is a perfect example of dynamical tunneling. And this is exactly what is happening in the system. And you can see that these orbits which are trapped look very similar to these orbits that we are seeing, which are taking a lot of time in order to get over classically. So what we believe is that these trapped orbits are sort of scarring, if you want, or shadow. These are the shadow orbits of these trapped orbits. Classically, they still are going to take a long time to escape, and therefore they become sequential. But the quantum actually finds a tunneling sort of pathway to get over and make them into. And that's exactly why you see this huge increases in these dynamically conserved fractions. So this is a patently quantum tunneling effect, if you want, that is happening. There are other classes also, but this is one of the interesting ones. Okay. Final question. Well, if this is a quantum effect, there are two protons, they're the same protons, right? They are doing this motion, right? Are they entangled? I mean, it would be ridiculous to use Wigner, to use entangled trajectories and not ask about entanglement, right? So this is a given. So it turns out one of the simplest thing we can do is actually calculate what we call as the linear entropy. This is not necessarily the best measure of entanglement, clearly, admittedly, but it's still a decent one in this pure bipartite system, as the technical name goes. This is a bipartite system, okay? And what we do is we actually trace the Wigner function over the antisymmetric mode, look at this reduced one, square it, and then construct this quantity, which is basically the linear entropy. And it turns out that this linear entropy, there's lots of studies and there are lots of interesting properties that this particular object has. Now, what I'm showing you here is this region where there is a large difference that I showed you in the dynamical concerted character, and a particular d value where there is a very small difference between classical and the quantum. And if you look at the case where there's a large difference, you will see that the linear entropy quantum, which is a measure of the entanglement, is showing very, very interesting interference effects, okay? Whereas the classical, which is a solid line, is essentially saturated pretty quickly. But if you look at where the classical and the quantum dynamical fractions are very close together, then you actually see that the classical and the quantum linear entropies are pretty much on top of each other. They're pretty close. So, therefore, this is an interesting thing. We don't completely understand it. But what we know is, for the first time, we are beginning to understand that the dynamical concerted character that could be happening in such systems, at least, there is an interesting link between tunneling and entanglement, both. Okay? And how exactly or what portion, what is this interplay between this is something fascinating. Okay? This is what we are trying to find out. Now, the final slide, and remember I told you I'll tell you what the connection of this is to Sati. Sati, of course, is my colleague, as all of you know, a very senior colleague. He's been pretty helpful all the time. In fact, when I came back from my first sabbatical, I had just finished my first work on dynamical tunneling. Sati heard about it and he said, why don't you write a review about this for international reviews in physical chemistry? Because he was on the editorial board at that time. I agreed. That was in 2005. It took me, at my own sweet pace, about 2 years to finish this review. So it appeared. And in 2010, actually, Taylor and Francis said, hey, your review seems like people are reading it. Why don't you guys write a book? And it turned out that myself and my good friend Peter Schlagek actually ended up writing this particular book. And if you've not seen it, there's not an advertisement. If you haven't seen it, just go and see this, because it's not about just chemistry. It has dynamical tunneling in the context of physics, of whispering gallery modes. And it goes back to the question Andrew asked about the water droplet being a cavity. It can support these whispering gallery modes, and there is very interesting effects that happen. So tunneling happens in optical cavities. It actually happens in physics in very interesting condensed matter system. Of course, happens in chemistry. So this book sort of, is a collection of articles by this. So thank you, Sati. So it seems like I've come one full circle, literally 20 years later, that this problem that we're looking at now seems to get connected up to dynamical tunneling and entanglement in an interesting way. So thank you very much and happy Saturday.
Swayam Prabha, Digital India, Educated India.